as Adam was mentioning, the idea is to get more discussion. So there's a lot of new data here that I would love everybody to discuss and give their opinion on. But the main thing we have been working on the last couple of years is on actinolite chemistry. We chose actinolite because it's a common mineral in IOA and IOCG deposits. And the idea is to use actinolite chemistry and see if we can get any information on its composition that relates to the hydrothermal evolution of these deposits. So why actinolite? I think one of the main good things actinolite has is that it occurs in pre and similarization stages in IOCG deposits. So what I'm going to show you today is all in Candelaria, but I just want to mention that it's not only in Candelaria where we see these different generations of actinolite. I think this photo here represents really nicely what I'm trying to show, where we see like really coarse grains of actinolite that are cut in fine grains of actinolite. So here we definitely see that there's at least 2 stages. And what I did was sample a really deep hole in the Candelaria deposit, which is the largest IOCG deposit in the Andean belt. I'm not going to give much information on the deposit itself because I want to stick to the 15-minute time frame. But I sample systematically this drill hole every 100 meters. And the good thing about this drill hole is that it cuts the main body of actinolite of Candelaria, so where we have all the copper mineralization, but it also is so deep that it goes out of the main ore body into the background, which is the background is mainly magnetite and actinolite alteration. So immediately we can see just macroscopically that there are 2 generations of actinolite. And the idea is to see if we can also see these generations just by looking at its chemical composition. So the first thing we did was look at the textures in actinolite grains, see if we could see any zonation or any different textures that could, represent more than 1 generation of actinolite. And it was pretty successful. Just looking at BSE images, we can see that we have replacement textures, overgrowth, and oscillatory textures of these different grains. Some of them which are very dramatic, as we can see in this grain over here that I'm going to be showing quite a bit. So the next step was to see if we could relate these zonations to difference in this composition. And yes, we see immediately using WDS quantified maps that we see differences in aluminum, magnesium, iron, calcium, just to give some examples. So these are all major elements. Same thing for this other grain and so on. So the idea here was not only, so the first thing we did was actually just use the magnesium and iron contents and use this as a proxy to estimate temperature based on a 2008 paper from Haroldo and Jenkins that uses the iron number to estimate temperature formation of actinolite in IOA deposits. So what we see first looking at spot microprobe data is that actually we see very dramatical differences in the temperature on one same grain of actinolite. Here we see in the center of this very zone grain that we have temperatures that are higher than 750 degrees Celsius. This geothermometer has a plus minus of 25 degrees, just in case. And then we see the overgrowths are more than 100 degrees Celsius lower than the core of the grains. So what I did next was actually look at all the different temperatures downhole. And what we see actually, if we look at the average temperatures of early textures, is that we see a gradient. We see temperature is going up as we go downhole. Also, if we correlate this with grades of iron, copper, and gold, we see that copper and gold are very correlated, but are pretty decoupled with iron. Iron grades actually are still really high once we are out of the main ore body, where we see the higher copper and gold contents. So what I did next was, we already used this geothermometer or proxy in the spot analysis that we did using microprobe. But the idea also was to try and use these WDS quantified maps and just use every pixel of these quantified maps as point data. So the idea is to apply this proxy using the iron and magnesium contents, but on an image. So basically, we did a pixel by pixel using the magnesium and iron concentrations. We applied a polynomial regression using Python, the same one that was used in the 2008 paper. And we get finally these really, really amazing temperature maps on actinolite. And we can see that each pixel represents a temperature in Celsius degrees, again, was this plus minus 25 degrees Celsius. And we can immediately see that the core of these grains is quite higher temperature than the overgrowth, and that we see very complex textures in terms of temperature. So we did this for all the temperature, all the mass we had, and we see strong variations within single grains. I think one of the most important things here that we did a very detailed work on the textures, so we can actually see which are the earlier textures, and we always see that the earlier textures tend to have higher temperatures than the later one. So what I did next was actually use all the data points, all the pixel points, and do a histogram with all the actinolite data, and we see very distinct clusters, mainly two clusters of temperature, where cluster 1, as we see over here, is higher temperature and is actually within the range of solubility of iron. So iron will be soluble at a higher thermal fluid that has this range of temperature. It is also a range of temperature that is very similar for IOA deposits. This not only used in actinolite chemistry, but also used in oxygen isotopes. And then we have a cluster 2 that is a lower temperature range and actually fits really nicely with solubility conditions of copper at a similar temperature range and also similar conditions of what we find in Candelaria. And we know again by this texture work that actinolite textures from cluster 1 are actually earlier than cluster 2. So what are the implications for this? And again, so we also have to think about when does copper comes into this story. We know it's soluble within the range of temperature of cluster 2, but once it goes down of this range of temperature of like approximately 570 degrees Celsius, it will start to precipitate chalcopyrite. So it fits really nicely that the cluster 2 actinolite represents a hydrothermal fluid where copper is soluble, and once it goes down in temperature from that range, it starts to precipitate chalcopyrite. So we can conclude or suggest that actinolites from cluster 2 will represent a copper-rich fluid, which would be the responsible for copper mineralization in the deposit. And again, one of the main things that we wanted to show is that this is not only geochem data, but we also see it in the paragenesis. We also see it in hand samples. And here we can see in cluster 1, where we have this magnetite and actinolite, which are really early. This sample over here is from over 1,000 meters deep from the Candelaria deposit. And then we can see really nicely this cluster 2, where we find actinolite very closely related to mineralization, in this case, chalcopyrite, and we can see also some pyrite. So we put all this information together, and not only this data, but also data from previous work that we've been doing in the Candelaria deposit to come up with a new genetic model of how the district formed. So again, this is an IOCG district, so our faults are really important. All the structural control in this district is by sinistral transpressional faults that have a north-northwest orientation, really strong. And we know by pyrite chemistry work that I did a couple of years ago that the main origin of the hydrothermal fluids is magmatic hydrothermal. So we have to think about a system that starts with a magmatic system that is pretty high temperature, that's accumulated, fluid rich in iron, copper, chlorine, and it's overpressured. So once we move the faults a first time, that the fluid that will ascend will be too hot to transport copper. So it will mainly precipitate iron in the form of magnetite with actinolite. And this will be more similar to an IOA style mineralization and also more widespread than our classical IOCG, which is mainly restricted to faults and permeable horizon. We can let this magmatic system or fluid accumulation go down in temperature. And once we move the faults again, the fluid that will ascend will be in that really sweet spot where copper is soluble. So we will not be only precipitating magnetite and actinolite, but we will also be precipitating chalcopyrite and pyrite. And again, we can repeat this where we finally end up making our Candelaria, where we can also at the end add the interaction with basinal brine fluids. One of the things we have realized, and I think with new data, is that the range of time where this happened is actually really large. We're talking about millions of years. So this magmatic system is probably not only one static magmatic system, but something pretty dynamic where we have a replenishment of the source, maybe of different magmas. And what I'm going to show next is actually indicating exactly that, not by using geochrom, but just looking at other elements compositional in terms of composition in actinolite. So one of the main things we see here is that this actually has really big implications for how we understand the IOCG and IOA model. So historically, we think that IOAs are the roots of an IOCG system, But what we're seeing here is it's actually, we can have an overlap of both systems where we have a dynamic source that is changing with different pulses that are being superposed one over the other. And this opens the possibility of exploring areas that are rich in IOAs for IOCG deposits. Normally we would think that if we see only IOAs, we will be too deep in the system to find an IOCG. And this is actually saying that that maybe not be the case. So basically we see an overlap between these two parts of the whole system. So just to finish very briefly, I want to talk a little bit about other elements that we see in actinolite. So not only all what I was showing before is all based in magnesium and iron. So what happens when we see other elements? So one of the main things we see is that when we start plotting elements that tend to replace each other in the actinolite structure, we see not only one linear trend, but actually two different trends. And these trends fit really nicely with what we were talking about between early and a main stage actinolite. And we see this in kind of complicated to understand because of the colors. I'm sorry because of that, but we can see that goes from lighter to more darker colors in terms of how deep the sample is. And we can see how all the darker colors are forming its own, its different trend from the lighter colors. So this is suggesting that we have two different fluids that are being involved in the system. So what I did here was do a lot of playing with different elements to see which elements could actually work and separate these early and main stage, also using ratios, and by the end also using some principal component analysis. And what we see is that the aluminium sodium ratio is actually really good to separate an early from a main stage event. And if we plot this against temperature, we can see very nicely that we have these two different clusters, and we can separate over here. But we can take this step, we can take the one step further and look at also trace elements. And for this, I was using scandium, which is an element that you will see later, has very complex zonations within the actinolite grains. And what we see is that this main stage mineralization, we can actually divide it into two clusters, two subclusters. And I'm going to show you next that these two subclusters actually have very distinct geochemical compositions. So we are talking about now that we have an early and a main stage textures in actinolite, but also this main stage is more complex than just one pulse or one episode. So I'm going to show you now some of the variations that we see, just looking at these three groups and how we can also see these in different compositional maps. So elements as aluminium, sodium, titanium, and fluor are pretty different and distinct between these three different groups. We see that titanium is higher in the early samples, as so is fluorine. We see that aluminium is quite higher in this main stage 1, and sodium is just going down from the earlier to the later stages. And we can see these zonations also in the compositional maps that show very complex textures. Just looking at aluminium, this is in log, just to make it more dramatic. We can see how we have a higher aluminium core, but then it has some parts that is lower, surrounded by higher. We also see some very neat oscillatory textures. And titanium, we see in some grains is higher in the core, in other it isn't. So we actually can understand that there's more than one event, and these actinolites are quite more complex than just, separating in two main groups. Looking at other trace elements such as gallium, vanadium, zircon, or scandium, we see that gallium is higher, again, this main stage 1, lower in the early stage. Vanadium is also higher in this main stage 1. So this is a great way of seeing how these two subgroups are very distinct geochemically. And scandium is very low in this main stage 2. And if we look again at the maps, we see some amazing zonations over here. This is the same grain always, where we see the core has oscillatory scandium zonation, then it has no scandium. We can see in vanadium that we have some rims of this core that are high vanadium, then it goes down. And we can see also very complex textures with the other grains, where we see that scandium is showing some amazing textures. And over here, we see other grains. This is a different one. We have some areas that are very high in vanadium, others are lower in vanadium, and has some very little scandium. So just looking at some metals, cobalt, nickel, and zinc. One thing I have to say, these actinolite have very, very little copper, like undetectable. So we're not using copper to understand copper. So we have to use a proxy. In this case, we're using zinc. So we can see that cobalt is quite higher in the early stage. Then it goes up actually in this main stage 2. nickel is higher in main stage 2 than main stage 1. And then we see that zinc is higher in this main stage 2. So we tend to see that the metals are actually higher in the second substage of the main stage. And we can see that also in the zonations really nicely, where we see that nickel is higher in the borders of the actinolite grains. In every example that we see that zinc also tends to be higher in some borders. This grain shows it really nicely. And we see that cobalt can be higher in this early stage, then lower, and then higher again. So it's pretty nice because we actually see a correlation between these box plots and the grains and their zonations. So here are some observations. And again, this is work in progress. I'm actually working on this manuscript now. So this is why I wanted to show it, that we see that the chemical composition of actinolite grains show more than 2 distinct groups. So it's more complex than we thought initially. The early stage actinolite, although has a higher temperature signature, which we saw before, this reflects in high titanium, but also a more magmatic signature, which reflects in high fluorine. And this makes sense with the calculated temperatures and also with a more similar composition or signature that we see in IOA systems. And this reflected by papers of Gisela Palma from 2019 and 2020. Vanadium is really interesting. So some sort of recent work interprets vanadium to be very redox sensitive in experimental data and riot acidic melts. Can we apply this to an IOCG system? I don't know. This is something that I'm thinking about. But maybe what is the changes in vanadium are showing a more reduced environment, which makes vanadium more compatible. And we could be seeing these redox changes actually looking also at these trace elements in actinolite that we know happen in IOCG deposits because of the iron oxides that we find. We see also higher concentrations of aluminum in magnetite in previous research that have been interpreted to indicate more hydrothermal conditions. So maybe the main stage actinolite grains, especially the ones that are early, have a higher aluminum, and this could indicate that we're moving from a more magmatic system from a more hydrothermal one. Then in cobalt and zinc in the main stage samples are higher in main stage 2. And what I'm doing here is actually suggest that zinc and copper, that we can use zinc as a proxy to understand copper, and probably mainly because their solubility is very similar at the conditions that we estimate for IOCG mineralization. So this main stage 2 could indicate the phase where copper mineralization occurred. The higher nickel in the borders of actinolite, we suggest that this could be a dissolution precipitation of sulfides, and we're actually getting the nickel from the sulfides that we know are pretty high in nickel from our previous pyrite work. And then the high scandium in early stage 1 and main stage 1 could be an indication of the source, that the source is high in scandium, and then we have a replenishment of the source. And then we see the scandium go down pretty dramatically in this main stage 2, and this could actually indicate a depletion of the same source. And we see this also in elements such as zircon and yttrium. So basically all of this is really helping us understand and further understand the complexity and evolution of these IOCG systems, and also shows that the use of actinolite as a proxy works really, really well. It has been a very good surprise working with this mineral. And just to finish with a high note, so we've been also looking and comparing actinolite composition with other IOA deposits from data that has been or previously published or not yet published. Only look at major elements, so using iron, magnesium, aluminum, and sodium. And actually, we can separate IOCG deposits from IOA deposits and also separate their different stages. So here we see in orange samples from Candelaria, we see the early, the early and the main stage. And then the early samples overlap really nicely with samples from La Higuera, which is an IOA system that is not only IOA, but has different stages that overlap, from El Romeral, and some even samples from Los Colorados, especially from one of the main ore bodies that is interpreted to be more hydrothermal than the other. And then we see another cluster of samples that are from Los Colorados, La Higuera, and Romeral that plot even higher temperature and have a lower aluminum sodium. So it seems to be that we can actually use actinolite chemistry as a proxy for classifying and understanding IOA and IOCG deposits, and showing that they go from something end member more magmatic to something more hydrothermal. So the idea of this is also using major elements. This has a huge potential as a pathfinder for identifying different deposits within the iron-rich family. So what comes next? Well, we have samples from more than 10 IOCG and IO deposits from the Andean belt. We have a really amazing sample set that we just started to work on. So we need to test them, we need to analyze, and we need to complete this plot, add more samples, and actually we think we can arrive to a point where we can actually have different area, parts of the plot that indicate IOCG versus IOA. And the idea is also to add samples from skarn deposits, and finally also test with samples from alkalic porphyry deposits that we know that are rich in actinolite. So basically this has been a whole talk talking about how good actinolite is and how it can help us understand these deposits. So thank you very much.